Hello everybody, welcome to Dr.K.Liu Math channel. This time we want to talk about vector field, line integration vector field over vector field, which is path independent. And if a vector field over a line integration is independent of the path, this is called path independent in line integration. In this case, whatever you use curve CU2 or CU1, then the result is the same, the line integration. And the necessary and sufficient condition for the line integration is path independent. Is f is actually the big F, the vector field is actually equal to the gradient function, gradient vector field of fx. Here and if and only if f is path independent. Here I want to prove this phenomenon. And if fx is, for example, in R3, which is from R3 to R, then gradient f is actually equal to fx, fy, fez. That means parcel f, parcel x, parcel f, parcel y, parcel f, parcel ez. Okay, then I start to prove for that if f vector field is, I should ignore I should skip the vector here, and then we can let f equal to fx, fy, fez, which is partial differentiation of fx around 1f, 1x, 1f, 1y, 1f, 1ez here. Okay, and let the curve R1 be any lice curve. I think I should be careful. Lice means a smooth continue, and the function over the curve is does not has is defensible. Okay, but I use terms lice from A to B. Here I draw the figure. This A, this B, from A to B. Okay, then and let A equal to R1A. A small letter A is means the time, and B equal to. That means the integration, the curve, the starting point is the parameterization curve starting from T equal to A, small a, then and R equal to A, like that. I don't want to repeat. Okay. Now, for this integration C1f dr, that means A, B, fx, fy, fez. Here, as I put the time t into the function, so this f1f is actually function of t. This is function of t. This is function t. Dot x pi t, y pi t, ez pi t, and dt. And that real notation actually of this path line integration is actually equal to this one. Okay, then and this part is function of t. Then that means we can write this is Okay, I write that. This part is function of t. Then we may assume this is d f dt times this dt. Then cancel these two and df. This is f. F here is x r1t from A to B. Then f put the b into the time t minus put the t into put the b into the t. Then this is actually b minus fb minus a. Then I also prove this one, this direction. Also prove the final result here. Okay. As the curve is this curve is arbitrary, any lines curve. Therefore, if I choose another curve, for example R2, actually that we can repeat the same process and get the final same result here. Therefore, we also prove that if f is a gradient vector of some function, then f is path independent. Okay, for the converse, if fdr is path independent, I may let f is equal to f1, f2, as f is vector field S3. Or in two-dimensional space, we can let f is f1, f2 only. And also let Rt be a parameterization, a line segment parameterization, a plus t times b minus a. For I check something for you. T equal to 0, R0 equal to a. T equal to 1, R1 equal to b. Therefore, this format is actually equal to 0 to 1, f1, f2, f3, dot x pi t, y pi t, z pi t, dt. And make this dot product together. We have f1 x pi plus f2 y pi plus f3 ez dt. And this is actually function of t. Function of t. We may let function of t. We may let function of t. We may let this this part is d something. For example, I call that phi over dt. Then in this case, we can conclude that f1, f2, f3 is actually equal to the gradient vector of phi. Phi is function of x, y, z. That is the proof of the converse. And as this is fundamental proof of the line the fundamental theorem of line integral. Therefore, please remember, if we have this condition, the result can be easily equal to fa minus fb. Here, I want to illustrate by these two examples. And this example, integrate y dx plus x dy. Actually, this is y. The vector field is y, comma x dx dy, and the curve is here. And r pi cosine t minus sine t. Therefore, This is equal to 0 pi over 2. Y is cosine t, sine t. Dx is equal to cosine t, dt. Dy is minus sine t, dt. This is cosine square minus sine square means cosine 2t. Integrate 1 over 2 sine 2t. This is 0. On the other hand, I try to another curve line segment from this point to this point. And here I use the parameterization curve is 0.1 plus t times this point minus this point. 1 minus 1. And this is 0. T. 1 minus t. Then our 1 pi means 1 minus 1. And this is equal 0 to 1 y. Yx dx dy. Y is 1 minus t, x is t, times dx is equal to 1 minus 1 dt. Then this is 1 minus t dt. Again, do the simple job here, the result also 0. Of course, I use two curves, not necessarily this is line path independent line integration. But if we, by using the theorem here, this theorem, I want to find the vector field is actually equal to this, the gradient vector of some function. The vector field is yx. Actually, this is equal to. If we consider fx y equal to x plus y, then 1f 1x is equal to y. 1f 1y is equal to x. Therefore, this y comma x exactly equal to vector field f, capital F. Then by theorem, by the fundamental theorem of the line integration, is equal to f, this 2 point 0 1 minus 1 0. 0 1 here is 0. 1 0 is his 0. Okay, I hope you can understand my presentation, why I present that the importance of the fundamental theorem of line integration, which fundamental line in theorem of line integral is equivalent to the fundamental theorem of calculus. It's very essential for multiple variable calculus. Okay, guys, hope you can enjoy this video. Okay, bye bye.